There is a hole in space 330 million light-years wide. Astronomers call it the Boötes Void, and it's real. Immediate takeaway, it's a region almost empty of galaxies. You could line up 2,000 Milky Ways across its diameter, yet inside you find only a few dozen lonely islands. Let's walk through how a nothing this big can exist. Here's the map, the physics, and why it matters. By the end, the void will feel surprisingly familiar, because the same rules shaping galaxies also carve out emptiness. So, giant nothingness turns into a powerful test of everything. Let's start with what a cosmic void actually means. Picture a night sky with stars, but they thin out dramatically. Between galaxy clusters, enormous bubbles form like froth in soup. A cosmic void is one of those underdense bubbles in space. It matters because emptiness outlines where gravity piled everything else. Early universe ripples left some regions slightly lighter than average. Gravity pulled matter toward heavier spots, evacuating the lighter patches. Over billions of years, the light patches ballooned into vast hollows. Dark energy then helped the gaps expand a bit faster. Most voids span 30 to 100 million light-years across. The Boötes Void dwarfs that at about 330 million light-years. Inside it, surveys found only dozens of galaxies, not thousands. Rule of thumb, voids show 10% of average galaxy density. This giant dips far lower, flirting with near-total emptiness. So a void means underdensity, and this one is extreme. Think foam in rising bread, where big bubbles merge and grow. Voids do the same, slowly merging into a few colossal basins. Their centers thin, their edges sharpen into filaments and walls. Galaxies ride those walls like cities along continental coasts. The middle stays quiet, and it remains eerily star-poor. Now picture a pie-slice map cutting outward from our position. Dots mark galaxies, distance stretches along the slice. That is a redshift wedge, a three-dimensional slice of space. It matters because those slices reveal structure without guesswork. Astronomers measure spectral lines, compute redshift, and infer distance statistically. Plotted together, the dots trace filaments, walls, and yawning gaps. In 1981, one wedge through Boötes showed a shocking empty sector. It spanned hundreds of millions of light-years along the slice. Within that sector, only a sprinkling of dots dared appear. Not the dense spray you expect from a healthy cosmic neighborhood. One-sentence recap, a map slice exposed a giant cosmic blank. Follow-up surveys extended the map, confirming the void's roundish extent. Edges look ragged, but the gulf inside stays strikingly clean. Different teams checked for hidden dust, selection bias, or bright star masking. Those artifacts would leave patterns, not a vast, coherent absence. The emptiness persisted across catalogs and instruments year after year. Even today, updated maps keep that sector hauntingly thin. So the map itself, building dot by dot, revealed the void. On the ground, huge mirrors stare from deserts and mountaintops. They feed light into spectrographs, which spread colors into precise fingerprints. A redshift survey is a census of galaxies by distance. It matters because distance turns sky dots into a real map. Spectral lines shift redder as space expands between us and galaxies. Measure that shift, convert to velocity, and estimate moving distance. Repeat this thousands of times and structure emerges statistically. Wedge plots are a favorite because they show depth intuitively. In Boötes, CFA astronomers plotted spectra for galaxies across one sector. They expected a peppered field, maybe clumpier in some bands. Instead, a cavern opened, almost featureless along a huge stretch. Later catalogs, like SDSS, confirmed the sparseness with deeper reach. Galaxy counts inside landed at only a few dozen. If density were typical, you would log thousands across that volume. Common mistake is, thinking dust hid the galaxies from view. Infrared checks still showed emptiness where dust would fade. So instruments did their job and the gap proved genuine. Different telescopes, different seasons, same unsettling lack of dots. That consistency is a scientist's favorite alarm bell for truth. Now shift scale and watch the universe as a growing foam. Gravity drives matter into knots, leaving basins high and dry. A void is a gravitational hill, not a well. That matters because matter rolls off hills, accelerating evacuation. Density drops inside, pressure gradients are negligible, expansion wins. The boundary becomes a ridge, where filaments and walls later sharpen. Voids merge as their ridges erode, creating fewer, larger basins. Inside, peculiar velocities point outward, like rivers flowing uphill. Simulations show speeds of hundreds of kilometers per second. Over billions of years, that clears the interior efficiently. Boötes became so underdense, merger history likely played a role. Smaller voids coalesced, sculpting a near-spherical desert by chance. Rule of thumb, hills empty fast, wells fill even faster. So dynamics push matter out, while geometry keeps the basin clean. Dark energy's gentle shove amplifies that outward flow slightly. It does not create voids, it just stretches existing ones. The center's gravity hardly tugs, so orbits avoid deep penetration. Only a few wanderers cross, usually bound to passing filaments. Travel to the edge where the desert meets a crowded shore. Galaxies here sip gas from filaments, like towns along rivers. A void galaxy is simply a galaxy living in deep underdensity. It matters because environment shapes how galaxies grow and age. With fewer interactions, disks stay undisturbed and bars evolve slowly. Fresh gas is plentiful along filaments, so star formation can persist. But deep interiors run dry, limiting growth for stranded dwarfs. Merger rates drop, metallicities skew low, and morphologies stay simple. Surveys report void galaxies with stellar masses half typical field values. Gas fractions can be higher, sometimes double similar mass peers. Star formation rates remain modest, not quenched like dense clusters. A few oddballs roam inside, lonely spirals far from any wall. So the rim feeds growth while the heart stays sparsely populated. Their histories read quieter, with fewer violent gravitational tides. That lets delicate structures survive, like thin disks and faint rings. Astronomers love these labs because nature runs a cleaner experiment. There's a famous cold blotch in the microwave background. Some linked it to a supervoid along the Eridanus line. A supervoid is a very large, but shallower, underdense region. It matters because temperature maps test gravity and dark energy. Photons crossing evolving potentials gain or lose tiny energy amounts. This integrated Sachs-Wolf effect imprints slight hot or cold spots. A big underdensity can yield a cooler patch after crossing. Teams measured the void, estimated depth, and predicted the imprint. The observed cold spot is larger and colder than the prediction. It likely needs random fluctuations on top of the void signal. Stacking many voids in maps shows a weaker average signature, so the effect is real, but the debate remains lively. Bottom line, supervoids tweak the background slightly, not dramatically. Boötes itself sits too far and too rounded to matter. Eridanus looks patchier, with multiple shallower basins along one sightline. Analyses disagree on depth, partly from method and catalog choices. Better surveys are tightening bounds, especially with new microwave data. Net result, the cold spot is interesting, not a crisis. So does a giant emptiness shatter our standard cosmological model? A model here means Lambda CDM, with cold dark matter and acceleration. It matters because rare extremes test the tails of the theory. Lambda CDM seeds structure from tiny Gaussian fluctuations after inflation. Evolve them forward, and you get a web of filaments. Statistics then predict how common big voids should be. Volume matters because rare giants need enormous space to appear. Simulations of comparable scale produce a few Boötes-like basins, maybe one per several cubic gigaparsecs depending on thresholds. The observable universe offers the volume, so a handful is plausible. Counts of smaller voids match predictions even more comfortably. Shapes and density profiles also line up with simulation templates. So far, the big desert looks extreme, yet statistically fair. Uncertainties remain in galaxy bias, which traces matter imperfectly. Void definitions differ across algorithms, altering diameter and depth counts. But crosschecks with lensing support a deeply underdense interior. More eyes and bigger maps keep the model on its toes. We started with a hole in space, impossibly big and quiet. It turned out to be a map, not a mistake. Gravity wrote its negative, drawing walls by emptying the basin. Boötes is rare, but it fits the universe's handwriting. These deserts make the cities stand out and tests sharper. If that changed how you picture the cosmos, stick around. I share new space stories weekly, with clear visuals and context. Next time we will chase another strange pattern in nothingness. Until then, look up and imagine the spaces between. They shape everything you see by what they leave behind.